So in this part, we'll actually apply what we have seen in part 1 and analyze this machine in DQ windings. And this is a dynamic analysis, but there's no control because that control would come, in fact, in chapter 5. So just as a brief review, what we had seen was that these 3 windings that we have, in reality, we can transform them into 2 windings, so one on d-axis and one on q-axis, and they're moving at some arbitrary speed omega d, which we can pick. And we also saw the number of turns for each of this, I'll be careful here, d and q windings here, of this factor here. And the same d and q windings are for both rotor and stator. Okay, and by taking the projection of these current vectors, we can find what the current should flow in these windings here, ISD, IRD, and so on, things like that. And we also saw the reason why we picked these to be orthogonal in this D and Q windings. So the flux from one winding does not link the flux to the other winding, and therefore we were very quickly able to write an equation like this for the stator D and Q and the rotor D and Q. All right, so with that background, and then we saw these transformation matrices, which take us from ABC currents to D and Q axis currents, winding currents, I should say, in the stator where theta dA, which is the D axis with respect to fixed stator A axis, and then similarly this transformation matrix, which takes us from the rotor currents ABC to D and Q axis winding currents in the rotor, and this time we take theta D capital A because that's the rotor A axis. All right, and we can go the other way around because these 3 currents in the phase ABC reference add up to 0, so we can, given this ISD and ISQ, we can compute ABC, and similarly in the rotor circuit. So we saw that earlier. And then we derived these voltage equations, and we did not go through that in detail, right, in the first part. But we can review it very quickly anyway. If we did that, just skip over it. So these are the equations in ABC phases, and then by applying these transformation matrices here, we can convert them into dq, voltage dq current, and then when it comes to ddt term, we have to do integration by parts, and that's where we came up with this speed term over here. And here you can see that the voltage in d-axis winding is due to the flux in the q-axis winding. So these are coupled equations. And similarly in the q-axis voltage, you can see that the speed term here is coming from the flux linkage in the D winding. Okay, and so these are in terms of omega D, these speed terms. And then when it comes to the rotor, RND and RIQ, both of these would be 0 if we have a squirrel cage machine. And here you can see that the speed term that comes in is omega dA, because in this case the d-axis is moving at a different speed, in fact slip speed, with respect to the rotor A-axis over here. So it's omega dA that comes in, but here also we have the coupling from the respective other windings here. All right, so those are the voltage equations here. And so we can then derive this per phase equivalent circuit by, it's in order to derive this, we should really, take omega d, we should choose omega d to be omega sync. This is in steady state, by the way. So this applies only in steady state. And omega dA, which is the slip speed here, is S times omega sync here. Okay. So with that, we can, simplify, and in steady state, the other thing to remember is the ddt terms that you saw in the dynamic equations earlier. These ddt terms, it's not easy to say that, ddt terms are equal to 0. And the reason is that if we go back to here, this drawing here, that all these space vectors that we have, including the d-axis and q-axis windings in steady state, they are all rotating at synchronous speed. So there is no relative speed between them. And that is the reason why the projection of these currents, for example, on their d and q axis would be constant, and therefore the flux linkages would be constant, and therefore there is no change in flux linkage with time in this reference speed of omega d equal to omega sync, and therefore d dt term is 0. And that also applies when we talk about calculating initial conditions later on. So what we do is that we can write equations for all the voltage equations for all the 4 windings we have. So that's the beauty of this DQ analysis, that previously we had 6 windings which were coupled in ABC reference frame, and their mutual inductances were dependent upon the rotor position. Whereas when we go to this DQ analysis, first of all, we have 2 sets of windings, which and each one has only 2. So q-axis winding is decoupled from the d-axis winding. So that's a beauty of this dq axis analysis. So we can write all the voltage equations here like this, also for the rotor circuit here. And so where is the rotor circuit voltage? This is for q-axis, and this is for the d-axis here. And the flux linkages here we can write. I don't need to go through it in detail. And then we can express these flux linkages in terms of the currents and mutual inductances. So we get these 2 equations here, and then we can make them into a space vector Vs dq by multiplying this second equation here by a factor of j here, right? And so we get this equation here, and then we know that a space vector in steady state has some relationship to a phasor in phase A. It's the same orientation, just a slight different amplitude. So we can write from this space vector equation Vs dq to stator phase A voltages and currents. And the same thing we can do for the rotor circuit. And then these 2 equations that we have, so let's look at this equation, the last one over here, which we get for the stator, and this one here for the rotor. And these 2 can be simultaneously satisfied if we have this per phase equivalent circuit as shown here. Okay, so we can see that if you have current here IA, this current IA over here, and the sum of them is flowing through here, and so we get exactly a circuit, a unique circuit in a way, that with the assumptions that we have made, that these 2 equations are simultaneously satisfied, and that's what per phase equivalent circuit we had derived actually in the first course. So it's no different because it's the same machine. So why should that be any different? So moving on here, then it's a matter of calculating electromagnetic torque. So in the past, the standard procedure has been to do a virtual displacement and then find the change in energy work and differentiate partial with respect to the angle by which it has moved. So that becomes somewhat tedious. So in this case, we are looking at it on a very physical basis. So I like to say that this is really a physics-based analysis of machines here. And we are in very good shape, because so if you want to calculate the torque on the rotor d-axis over here, rotor d-axis. So here is the rotor d-axis winding over here, and it's represented by just 2 conductors, this one and this one here, concentrated conductors, with an understanding that it's really a distributed winding in space, cosinusoidally here. So we can calculate what the flux density is due to the current in the Q winding, ISQ over here and IRQ over here. Okay, so that's really the, the flux that is being produced that cuts these conductors here for the dewinding, I should say, on the rotor and produces a torque on this rotor here. So that's what we want to calculate, and we can make use of that torque expression from chapter 10 of our previous book, which is used in our course, where we talk about the torque expression for permanent magnet DC motors. So it's no different than that, except the number of turns per phase may be different here, and so just about. So that's the only difference. So if you go through that expression, I'll not go through in detail here. You can work that out. The torque that we get being produced on the rotor on in a counterclockwise direction is given by this expression here. So we can do the same thing for the torque on the rotor Q-axis here. And in this case, this rotor Q-axis right here is represented by these two uh, conductors over here, but again it's sinusoidally distributed, and this is being acted upon by the currents in the it should be being acted upon by the currents okay, in the d-axis. So you have ISD here and IRD over here. So these two windings are producing a flux, and this flux is then cutting these two conductors here, which are for the q-axis, right? So following an analysis very similar to that we did for the d winding, we can do that for the q winding. And again, the counterclockwise torque expression that we get is given here. So the total torque that we have on the rotor, being a linear system that we have assumed, is really the addition or superposition of these two torques here. So the total electromagnetic torque in a counterclockwise direction we have is due to the torque on the d-axis of the rotor and q-axis of the rotor. And we can plug in those expressions here in terms of flux linkages and currents, and we can change flux linkages to currents. Then we get this expression here. So this is the instantaneous, so to speak, electromagnetic torque due to depending upon the instantaneous values of these four currents over here, right? And so taking all that together, we have this electromechanical equation where this electromagnetic torque is acting on the rotor, and the load torque is opposing that electromagnetic torque, and the difference of those two is acting on this rotor plus whatever load is connected to it divided by the inertia of that system. Here we are ignoring the damping, is this acceleration, which is ddt of mechanical speed here. So we have to make sure that we make a distinction between omega m and omega mechanical, because omega m is p over 2 times the mechanical speed here, right? So for a two-pole machine, they are equal. Otherwise, they are not equal. Okay. So now, we once again look at what we have earlier derived, the flux linkages in d-axis in terms of d-axis currents, flux linkages in the q-axis windings in terms of q winding currents here, and therefore we can combine these two and we can come up with a common matrix that relates the currents in these DQ windings to the flux linkage in these DQ windings by this matrix M over here. And then we can invert this matrix M to go the other way. So that is shown over here. So if we are given, or in our simulation, we end up with calculating flux linkages by using this inverse matrix, we can go to the current matrix over here. And so again, the dynamic equations which we have derived earlier, they are no different, except we write it by putting this ddt term of flux linkages on the left-hand side, and what remains is on the right-hand side over here. And we're just trying to collect all the expressions we have derived that we will use. So here's the torque expression, and here's the electromechanical equation, and the only equation that is not missing is this here, that is 2 over P omega M, or the other way around. So, but so that's the only equation. So now, you know, let's say we are given that a machine is operating in steady state, okay, and suddenly a torque disturbance, load disturbance occurs at a certain instant of time. So wouldn't it be nice to have this machine be running in steady state from get-go rather than starting from, a black start, so to speak, a cold start, cold start, where there's no flux, no voltage applied, anything, and then machine comes to a steady state, and then at certain instant of time afterwards, we apply a load torque disturbance. We can do that, but it might take a while to bring this machine to steady state. So wouldn't it be nice to, depending upon what problem you're solving, it may be nice to be able to calculate the steady state initial conditions. So we can do that by using the fact that in steady state, if we choose the right speed for D-winding, omega D, let's say, is omega sync in steady state. So so using that, we saw that the ddt term for the flux linkages is 0. Okay, so getting rid of those, we can write these voltage equations over here. We can write these voltage equations in the form of a matrix equation like this here, and we can see that we can, given these voltages, which may be the case because we may be given ABC voltages, and by using those transformation matrices, we can find VSD and VSQ, and then applying this inverse of this matrix here, multiplying it, this vector by this inverse of this matrix, we can find these currents ISD, ISQ. And also we know the relationship between these currents and the flux linkages given by this matrix M, which we have seen earlier. So we have seen everything here, right? But these things we can use these equations in steady state to calculate initial conditions, where we observe that with this choice of omega D, these terms are 0 here. So that makes it easier, but certainly you can choose whatever reference speed for the D-axis you want, but you have to live with the consequences. Okay, so this is what is shown in this Simlink-based simulation here. We have these 3 voltages coming in, right? And then we need to know theta dA here. So that is coming back from feedback here, but we need to know theta dA in order to transform these ABC voltages in VSD and VSQ over here, and then using this omega D, which also needs to be coming back from the output, we can calculate the flux linkage in the stator, and the same thing in the rotor circuit. The D and Q axis voltages are 0, because if it's a squirrel cage rotor, VRD and VRQ are 0, and in this case we need the slip speed omega dA. Maybe do not want to use the word slip speed. Let's just call the axis of the speed of D axis with respect to rotor A axis. Okay, omega D capital A. So again, very similarly, we can calculate using the equation that we had described earlier. We can calculate the flux linkages in the rotor D and Q windings over here. So if you combine these, we get all these flux linkages in all 4 windings, and then we can, the expression we saw, we can calculate the currents in all 4 windings, and we can demux them, as they call, the D-axis and Q-axis stator, and D-axis and Q-axis rotor currents over here. Okay, so we can get those, and then we can calculate the electromagnetic torque here by knowing these currents over here, all 4 currents, and we saw the expression in terms of currents. We can get the electromagnetic torque, and we subtract the load torque, T sub L, so there's a minus sign here you can see. We can subtract that, and the difference of that acts on the inertia, and that gives us the ddt of this omega mechanical. So here is an integrator. So that gives us the mechanical speed, and you multiply that by number of poles divided by 2, and that gives us the speed in electrical radians per second. And you can see that that subtracted from omega d here gives us omega dA over here, right? So everything that we need, and then this omega d, when you integrate that, that gives us theta dA. Okay, so everything that we need to close the loop here is available in the simulation. So when we run this simulation, and we need to first calculate the initial conditions, so that may be given as a MATLAB file. So you have to double click here on the start button over here to get those initial conditions into the workspace, and those initial conditions are then used in the integrators in this simulation based on Simulink here. So so we just need to start plot over here, and then all these results come out here. So it becomes a very easy process here, and so it's a very good idea to see that as a result of a low torque disturbance. So low torque and electromagnetic torque plotted here, and electromagnetics plotted in blue, and low torque that I'm drawing in red, let's say, is like this. They're equal in steady state, and then low torque disturbance happens, and the low torque drops, let's say, as a step. It goes like this over here in red. Okay, so what happens to electromagnetic torque? Well, it doesn't exactly drop. It oscillates and then settles down to the steady state, new steady state value of the load torque here. And the same thing for the speed. The speed is constant here, and suddenly when this low torque disturbance occurs, the speed oscillates and then stays. It comes to steady state over here. So as you can see here, there's no controlling of speed here. It's a totally operating in open loop, so to speak. And so the results here are obtained using D and Q axis winding analysis, as opposed to calculating these results in ABC when the machine is modeled in ABC reference frame. But it's the same machine, so the results should be identical. There should be no difference whatsoever. So that will be very satisfying to convince yourself that you model it first in ABC reference frame, and that was perhaps an example or homework problem, and then you get the results, and then we do this with the simulation using D and Q axis winding analysis, and we get the same results. So we should stop here, and what we'll do is in chapter 4 we'll get a more of a physical basis how to control this machine. So imagine that this low torque disturbance occurs, but you want to keep the speed constant. See, speed does not remain constant here. It was here in steady state before the load disturbance, and then it goes to steady state over here. These are two different values. But you can imagine a process where even when a low torque disturbance occurs, you want to keep the speed constant. Let's say that's an example. That's what you want to do. Well, you want to do what is called vector control. And that vector control in a mathematical form, we'll see it in chapter 5. When in between, in chapter 4, we'll see qualitatively, or physically I should say, maybe physically is a better word, get a physical basis of how that control is possible, where we can keep the speed constant even when this low torque disturbance is occurring. So that will be a very difficult thing to do if we had not done this D and Q axis analysis. But so that's really the benefit of this analysis. So let's stop here, and then we continue on with chapter 4 in the next module. Yeah, thank you. So David, we went too fast, but but